How did the universe grow up? This simple-seeming question was one that puzzled humanity endlessly for all of our civilization's history, right up until the middle of the 20th century. It was at that point that the cosmic microwave background was discovered, where it was quickly linked with being the remnant glow of long wavelength predicted by the Big Bang. Since that time, we've enhanced and refined our understanding, determining the age of our universe and what it's made of at present. This knowledge is enough to give us a set of expectations. How and when we think the universe should have formed stars, galaxies, and even groups and clusters of galaxies, paving the way for our modern cosmic web to take shape. But the key specifics of precisely how fast the universe grew up on stellar, galactic, and supergalactic scales remained beyond the reach of our greatest prior observatories like Hubble. But James Webb is changing that aspect of the story. For the first time, we're not just guessing, but actually seeing how the universe grew up. Thanks to the incredible capabilities of James Webb, we're constructing a more complete, comprehensive, and accurate picture of how our universe went from a small, star-free, almost perfectly uniform state to our tremendous, galaxy-rich cosmos of today.
We are going to discover incredible things that we never imagined.
But while James Webb is filling the gap in our understanding of the universe, it also detected several mysterious objects that could break cosmology.
That we can see with JWST, or we think we're seeing, are bigger than we had expected.
Is the discovery of unimaginably distant objects a mirage or a revolution? Stay tuned as we reveal the mysteries of these extraordinary discoveries and delve into the world shattering revelations brought to light by James Webb. It's hard to believe, but it was only 100 years ago, back in 1923, that humanity first realized that the Milky Way galaxy didn't encompass the entire universe. That key discovery was made by Edwin Hubble, who, while observing what was then known as the Great Nebula in Andromeda, recognized that a periodic light flower he was seeing wasn't a nova, as he originally thought, but was rather a variable star located much farther away than any of the Milky Way's stars. It was the first slam-dunk evidence that these spiral and elliptical nebulae, observed for centuries, were actually galaxies all unto themselves, or as they were called at the time, island universes. Today, we know that the observable universe contains several trillion galaxies, with the earliest dating back to when the universe was less than 3% of its present age. With our own naked eyes, we can only see the stars and nebulae of the Milky Way and a few other nearby galaxies, all within our gravitationally bound local group. But thanks to a variety of observatories, including the Sloan Digital Sky Survey, Hubble, and now James Webb, we can see what the universe is like both near and far. And while we've only mapped out a tiny fraction of all the galaxies that exist, we've seen enough that we can not only describe what the universe is like at each moment in cosmic history, but we can compose three-dimensional visual reconstructions that show how the universe's galaxies appear and grew up over time. As you can clearly see from these videos, galaxies come in a great variety of shapes, sizes, and groupings, with large numbers of giant elliptical galaxies found within rich galaxy clusters, and the more familiar spiral shapes found more commonly on the outskirts of galaxy clusters, and in what astronomers call the field, or the regions of space that aren't associated with any rich clusters. This shows off what the universe looks like today, but if we want to know what the universe looked like in the past, and describe how it grew up, we need to look even deeper. One of the most remarkable parts of the cosmic story is that the universe, as it is today, is not the way it's always been. Our universe started out in a very different state than what we experience today. Instead of being sparse, filamentary, cold, and with rich evolved galaxies that are grouped and clustered together, the early universe was different in every way. Today, we observe that the universe is expanding, and we know that the rate of cosmic expansion is directly related to the overall energy density of space itself. Well, back at earlier times, the universe was denser, expanding faster, less clumpy and clustered, and also hotter, as the photons within it hadn't been stretched to the long wavelengths they now possess at present. One of the most remarkable types of studies we've been able to perform are comparative galaxy studies, looking at the galaxies found within the universe today and comparing them to galaxies found farther away and whose light was emitted at significantly earlier epochs in the universe. Unsurprisingly, we find that galaxies have evolved from a population-wide perspective significantly over the billions of years that have passed. One of the best ways to see this for ourselves is to perform what's known as a pencil beam study of the distant universe. In this technique, we observe one single tiny region of sky that happens to be devoid of any relatively nearby stars or galaxies. We observe it for long durations of times in a variety of wavelengths, including, and perhaps especially, in long infrared wavelengths of light, wavelengths that are excellent for discovering and imaging galaxies whose starlight has been stretched to longer wavelengths by the cumulative expansion of the universe that occurred since their light was first emitted. Throughout the 1990s, 2000s, and 2010s, the best views of the distant universe in this fashion came courtesy of the Hubble Space Telescope. The deepest view ever taken, prior to the launch of James Webb, was of the Hubble Extreme Deep Field, which observed a region of space so tiny that it would take 32 million comparably sized regions to cover the entire sky. In that little narrow pencil beam of space, more than 5,000 galaxies were revealed. They span all of cosmic history, from the relatively nearby universe to more than 13 billion years ago, much closer to the Big Bang itself than to the present day. By measuring the distances to these galaxies, we've been able to recreate what a three-dimensional fly-through of those galaxies, near and far alike, would look like. But there are several limitations from taking this approach. First off, we aren't seeing all of the galaxies out there. Even in this deep view, we're probably only seeing somewhere around 1% of all of the galaxies that are out there. Most of them are small and faint, whereas the easiest ones to see are big and bright. We know we are significantly biased in what we're able to detect. Second off, most of the galaxies that exist are probably satellite galaxies that orbit around the large bright ones, and we don't have the sensitivity to observe them. We struggle to even count the number of galaxies in our own local group, so the small, low-brightness galaxies that represent the most common type of galaxy are largely invisible. Third, for the first 550 million years after the Big Bang, less in some places, more in others, the universe was filled with light-blocking neutral matter, similar to what's found in the disk of the Milky Way. We can only see the light from these early epochs that's bright enough to pierce through that light-blocking veil. And fourth, the brightest galaxies of all are the ones that are actively forming stars over the entirety of the galaxy itself, a starburst galaxy. The earlier we look, the more likely we are to be seeing a starburst galaxy, and the more likely it is that the starbursting has been triggered by a major merger of two comparably sized galaxies. Although all prior observatories have succumbed to these limitations, including even Hubble, this is precisely the class of observations that NASA's James Webb Space Telescope has been designed to overcome. Looking at the universe with larger eyes optimized for infrared wavelengths and for penetrating this light-blocking neutral matter, James Webb has discovered many galaxies that have surpassed even the limits of Hubble. Observing programs like JD's, Sierra's, GLASS, Panoramic, Cosmos Webb, and more are showing us how the universe grew up like never before. And unsurprisingly, it's not only taught us some incredible science so far, shattering several cosmic records in the process, but it's enabling us to visualize the young universe as never before. as Steve Finkelstein, principal investigator of the SARES collaboration, has put it. The sheer number of galaxies that we're finding in the early universe is at the upper end of all predictions. We're used to thinking of galaxies as smoothly growing, but maybe these stars are forming like firecrackers. Are these galaxies forming more stars than expected? Are the stars they're making more massive than we expect? These data have given us the information to ask these questions. Now we need more data to get those answers. Indeed, when James Webb finally started taking data, a number of extremely suggestive candidate galaxies for most distant of all emerged, but it would take spectroscopic confirmation to be certain of properties like distance. Looking in the James Webb Space Telescope, Advanced Deep Extragalactic Survey, or JADES field, a series of galaxies were imaged spectroscopically, with a new record holder emerging at a confirmed redshift of 13.2 and a corresponding age of the universe of just 320 million years at the time. Other ultra-distant galaxies have been found by James Webb, with multiple other JADES galaxies found younger than 500 million years, and significant competitors in the same class of distances. The galaxy JADES GSZ13-0 is the name of the current record holder, but it's fully expected that with more data, deeper data, and greater sky coverage, this record will soon be broken, and likely many times over before all is said and done. One of the largest, deepest views that James Webb has taken of the universe, at least so far, comes from the SARES collaboration, the Cosmic Evolution Early Release Science Survey. By surveying a very large area of sky of 100 square arcminutes, SARES aimed to photometrically observe extraordinary numbers of galaxies within that field. The rationale is that this photometric survey would identify a number of galaxy candidates that might be among the earliest and most unusual galaxies in the universe, and then the best candidates would be able to be followed up with Webb's spectroscopic capabilities. Against all expectation, the premier space observatory has found something very strange. It didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. As Michaela Bagley of the University of Texas, one of the leading CER's researchers, said, "The theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright, that early." Such the high number of early galaxies detected suggests that there's something we don't yet understand about galaxy formation, and how that process has changed between billions of years ago and now. The fact that the galaxies are brighter than expected is intriguing too, and could have several explanations. These galaxies could actually be giving off more light, or they could be more massive, or it could be a combination, as the two factors are related. The early universe had galaxies with potentially as many stars as the Milky Way, and we don't have an explanation for how these stars could have formed so early or in such great numbers. There's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. On the other hand, note that the most distant galaxies that we've ever discovered are just the tip of the cosmic iceberg, the brightest and most massive galaxies found at these extreme reaches of the universe. As James Webb continues to collect more and more data, the distant universe will continue to come into focus, answering some of our present questions and opening up new avenues to investigate. A full understanding of our universe, from the earliest times imaginable all the way to the present day, is finally closer than ever to being within reach. Interestingly, beside the most distant galaxies, most recently, James Webb stuns the whole world with new high-definition look at exploded star. Look at this! Supernova remnant Cassiopeia A, or Cass A, gleams in a new image from James Webb like a shiny round ornament ready to be placed in the perfect spot on a holiday tree. For those who don't know, A supernova remnant is located 11,000 light-years away in the constellation Cassiopeia. It's estimated to have exploded about 340 years ago from our point of view. While all is bright, this scene is no proverbial silent night. Webb's near-infrared camera, or NIR cam view of Cas A, displays this stellar explosion at a resolution previously unreachable at these wavelengths. This high-resolution look unveils intricate details of the expanding shell of material slamming into the gas shed by the star before it exploded. Cas A is one of the most well-studied supernova remnants in all of the cosmos. Over the years, ground-based and space-based observatories, including NASA's Chandra X-ray Observatory, Hubble Space Telescope, and retired Spitzer Space Telescope, have assembled a multi-wavelength picture of the object's remnant. Astronomers have now entered a new era in the study of Cas A. In April 2023, Webb's Mid-Infrared Instrument, or MIRI, started this chapter, revealing new and unexpected features within the inner shell of the supernova remnant. Many of those features are invisible in the new NIR cam image, and astronomers are investigating why. Infrared light is invisible to our eyes, so image processors and scientists translate these wavelengths of light to visible colors. In this newest image of Cas A, colors were assigned to different filters from NIR cam, and each of those colors hints at different activity occurring within the object. At first glance, Webb's NIR cam image may appear less colorful than the MIRI image. However, this simply comes down to the wavelengths in which the material from the object is emitting its light. The most noticeable colors in Webb's newest image are clumps represented in bright orange and light pink that make up the inner shell of the supernova remnant. Webb's razor-sharp view can detect the tiniest knots of gas, comprised of sulfur, oxygen, argon, and neon from the star itself. Embedded in this gas is a mixture of dust and molecules, which will eventually become components of new stars and planetary systems. Some filaments of debris are too tiny to be resolved by even Webb, meaning they are comparable to or less than 10 billion miles across. In comparison, the entirety of Cas A spans 10 light-years across, or 60 trillion miles. According to Danny Milisavljevic of Purdue University, who leads the research team, with near-infrared camera's resolution, we can now see how the dying star absolutely shattered when it exploded, leaving filaments akin to tiny shards of glass behind. It's really unbelievable, after all these years studying Cas A, to now resolve those details, which are providing us with transformational insight into how this star exploded. When comparing Webb's new near-infrared view of Cas A with the mid-infrared view, its inner cavity and outermost shell are curiously devoid of color. The outskirts of the main inner shell, which appeared as a deep orange and red in the MIRI image, now look like smoke from a campfire. This marks where the supernova blast wave is ramming into surrounding circumstellar material. The dust in the circumstellar material is too cool to be detected directly at near-infrared wavelengths, but lights up in the mid-infrared. Researchers say the white color is light from synchrotron radiation, which is emitted across the electromagnetic spectrum, including the near-infrared. It's generated by charged particles traveling at extremely high speeds, spiraling around magnetic field lines. Synchrotron radiation is also visible in the bubble-like shells in the lower half of the inner cavity. Also not seen in the near-infrared view is the loop of green light in the central cavity of Cas A that glowed in mid-infrared, nicknamed the Green Monster by the research team. This feature was described as challenging to understand by researchers at the time of their first look. While the green of the Green Monster is not visible in NIR cam, what's left over in the near-infrared in that region can provide insight into the mysterious feature. The circular holes visible in the MIRI image are faintly outlined in white and purple emission in the NIR cam image. This represents ionized gas. Researchers believe this is due to the supernova debris pushing through and sculpting gas left behind by the star before it exploded. Researchers were also absolutely stunned by one fascinating feature at the bottom right corner of NIRCam's field of view. They're calling that large striated blob baby Cass A, because it appears like an offspring of the main supernova. This is a light echo, where light from the star's long-ago explosion has reached and is warming distant dust, which is glowing as it cools down. The intricacy of the dust pattern and baby Cass A's apparent proximity to Cass AA itself are particularly intriguing to researchers. In actuality, baby Cass A is located about 170 light-years behind the supernova remnant. There are also several other, smaller light echoes scattered throughout Webb's new portrait. Notably, this isn't the first time James Webb has turned its sharp eyes on a supernova. Just a few months ago, the time machine has gazed at the Crab Nebula, a supernova remnant located 6,500 light-years away in the constellation Taurus. Since the recording of this energetic event in 1054 CE by 11th century astronomers, the Crab Nebula has continued to draw attention and additional study as scientists seek to understand the conditions, behavior, and after-effects of supernova through thorough study of the Crab, a relatively nearby example. Using Webb's NIRCam and MIRI, a team led by T. Temim at Princeton University is searching for answers about the Crab Nebula's origins. At first glance, the general shape of the supernova remnant is similar to the optical wavelength image released in 2005 from NASA's Hubble Space Telescope. In Webb's infrared observation, a crisp, cage-like structure of fluffy gaseous filaments are shown in red-orange. However, in the central regions, emission from dust grains, yellow, white, and green, is mapped out by Webb for the first time. Additional aspects of the inner workings of the Crab Nebula become more prominent and are seen in greater detail in the infrared light captured by Webb. In particular, Webb highlights what is known as synchrotron radiation, emission produced from charged particles, like electrons, moving around magnetic field lines at relativistic speeds. The radiation appears here as milky, smoke-like material throughout the majority of the Crab Nebula's interior. This feature is a product of the nebula's pulsar, a rapidly rotating neutron star. The pulsar's strong magnetic field accelerates particles to extremely high speeds and causes them to emit radiation as they wind around magnetic field lines. Though emitted across the electromagnetic spectrum, the synchrotron radiation is seen in unprecedented detail with Webb's NIRCam instrument. To locate the Crab Nebula's pulsar heart, trace the wisps that follow a circular ripple-like pattern in the middle to the bright white dot in the center. Farther out from the core, follow the thin white ribbons of the radiation. The curvy wisps are closely grouped together, outlining the structure of the pulsar's magnetic field, which sculpts and shapes the nebula. At center left and right, the white material curves sharply inward from the filamentary dust cage's edges and goes toward the neutron star's location, as if the waist of the nebula is pinched. This abrupt slimming may be caused by the confinement of the supernova wind's expansion by a belt of dense gas. The wind produced by the pulsar heart continues to push the shell of gas and dust outward at a rapid pace. Among the remnant's interior, yellow, white, and green mottled filaments form large-scale loop-like structures, which represent areas where dust grains reside. The search for answers about the Crab Nebula's past continues as astronomers further analyze the Webb data and consult previous observations of the remnant taken by other telescopes. Scientists will have newer Hubble data to review within the next year or so from the telescope's re-imaging of the supernova remnant. This will mark Hubble's first look at emission lines from the Crab Nebula in over 20 years and will enable astronomers to more accurately compare Webb and Hubble's findings. But even with all this information, there's still a problem that emerges when it comes to the Crab Nebula, the problem of mass. Astronomers are a big fan of the idea that a star's initial mass, the amount of mass that it has when it's born, is what determines its eventual fate. We know that this is largely true, as stars like the Sun, which generally includes stars between 40% and 800% the mass of the Sun, will burn through their core hydrogen, evolve into red giants, begin fusing helium in their cores, and then will gently die, blowing off their outer layers into a planetary nebula while their cores contract to form a white dwarf. The lowest mass stars, which include stars below 40% of the Sun's mass, will have time to fully convect, bringing burned material out of the core and into the star's outer layers, while bringing new hydrogen-rich material into the core. When these stars run out of hydrogen, they won't get hot enough to fuse helium, leading to a state of slow contraction, ending in a white dwarf. But the highest mass stars, born with 8 solar masses of material or more, will not only ignite hydrogen and then helium burning in their cores, but will go on to fuse carbon, neon, oxygen, and then silicon and sulfur, eventually dying in core collapse supernovae, leading to a neutron star for the lower mass varieties and a black hole for the more massive ones. That's where the big puzzle arises. There just isn't enough mass in the Crab Nebula, as inferred by these multi-wavelength observations, to explain its core collapse supernova and neutron star fate. The Crab pulsar, or the neutron star at its core, comes in at only 1.4 solar masses. From all the previous multi-wavelength data, we've been able to constrain the mass of the Crab Nebula, the nebulous material that doesn't include the central pulsar, to be between 2 and 5 solar masses, with obviously a fair amount of uncertainty there. But observations at greater distances around the nebula, where it's plausible that a shell of material could have been blown off in earlier stages, reveal a complete absence of any detectable material at all. There's no shell, plasma, or diffuse gas present to the absolute limits that our instruments can see. Even if we take the high mass value for the Crab Nebula, that still doesn't give us enough matter or material to trigger a core collapse supernova. There's got to be a flaw in our understanding somewhere, but exactly where is a big mystery. Could we be modeling the nebula wrong? If so, improved data can help us better estimate the total mass of the Crab Nebula. Could we be measuring the mass of the neutron star incorrectly? It's possible, but not by that much. The most massive neutron star ever found is only slightly heavier than 2 solar masses. Could there be material that was ejected long ago that's now been blown away? Perhaps. But that doesn't align very well with our understanding of stellar evolution in the late stages of a massive star's life. Could we be misunderstanding the conditions for a supernova? It's unlikely, but we've observed so few in detail that we have to consider it. Fortunately, we're about to get an assist from the full James Webb view, now finally available, of the Crab Nebula. The greatest new detail that's finally revealed with Webb imaging, something that quite notably James Webb's predecessor, Spitzer, could not reveal, is the first complete and comprehensive map of the dust distribution within the Crab Nebula, since the spectral features that reveal individual elements only apply to individual atoms, not to dust grains that may contain those elements. It's possible that we've failed to sufficiently account for dust in previous observations. As you can see, above the central yellow, white, and green filaments that appear in Webb's infrared image are dust-dominated and could be incredibly rich in material. Also, in Webb images, as opposed to the optical Hubble images, you can see what appears as grayish-white smoke filling in the interior of the cavity carved by the expanding gases. This isn't smoke by any means, but rather a phenomenon known as synchrotron radiation, where fast-moving electrons are accelerated by a strong magnetic field, and the action of that magnetic field causes the electrons to radiate electromagnetic radiation as they pass through the magnetic field. It just so happens that the wavelength range that the synchrotron radiation comes in matches the wavelengths that James Webb is sensitive to. On the outskirts of the nebula, you can see that the smoke-like wisps are curved and pinched, like they're being funneled into a central disk-like shape. While there are numerous possible explanations for this appearance, one tantalizing one is that there's a belt of dense gas confining where the supernova's winds can flow. This is another possible store of massive material that has gone undetected thus far. There are also hotter, heavier elements revealed by Webb observations, particularly on the outskirts of the nebula. The red-orange filaments of gas seen by James Webb trace out doubly ionized sulfur atoms, which peter out at smaller distances than the lighter hydrogen atoms that Hubble was sensitive to, farther toward the nebula's outer edges. But perhaps, most interestingly, there are novel details revealed about the very heart of the nebula, in the region where the pulsar is located. The smoke-like wisps located toward the center trace out the magnetic field lines created by the central pulsar, and you can see many curved wisp-like features all grouped together, indicating the locations where the magnetic field is strongest. This represents material still being transported away from the central regions of the nebula, farther toward the outskirts. You can also see by looking at the full field view of these images that there's an asymmetry. The filaments appear to be lengthened toward the upper right of the pulsar, while simultaneously being relatively shortened in the opposite direction. Although it's still worth additional efforts investigating this phenomenon, it's notable that the pulsar itself is moving toward the top right of the nebula. Perhaps the extent of the nebula has something to do with the motion of the central stellar remnant. Hubble hasn't taken another look at the Crab Nebula since the early 2000s, more than 20 years ago. But that's about to change. Just as James Webb is observing the nebula now, it's important to get simultaneous data from Hubble in order to paint a more complete picture of this fascinating region of the sky. Perhaps with new, superior data from both observatories combined, we'll not only be able to map out the various details within it, but come up with a more satisfactory accounting of where all the mass is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.